If you want to have a comprehensive logistic regression, you definitely can do it with JASP for binary logistic regression. But if you want to do logistic regression for multinomial or ordinal logistic regression, maybe SPSS would be a better software for now if you have access. But if not, still JASP will give you some basic statistics for those as well. But there is no consent for binary. Logistic regression can be done very well with JASP as long as you are focused on binary logistic regression. So it's easy going to regression, logistic regression, and as you can see, it's just about the binary logistic regression. JASP doesn't specify that, but this function is only covers binary logistic regression. Like for example, if I put the ordinal variable here, you see that you get some errors for that. But so I can put the binary version of my dependent variable, that is depression, that with two levels. 0 is a non-clinical level of depression, 1 is clinical level of depression. So I put my IV, my DV here. And then my IVs, my continuous IVs, because they are continuous, I put it in covariate. If they were categorical, I would put them in factor. So I also need to tick a few boxes here, like going to statistics. I want to make sure that the confusion matrix is ticked. The estimate should be ticked by default. I also need a specificity, need sensitivity that I will explain them later. And I also odds ratio, that is the most important value that I want for my hypothesis testing. I also need to tick confidence intervals, and confidence intervals is specifically for odds ratio. Otherwise, it would present that for other statistics. So you should have confidence intervals and tick the odds ratio scale. And also, I want to check the assumption of multicollinearity. As you remember, I mentioned that JASP can do multicollinearity, can check multicollinearity with the minus. I can see even for binary logistic regression, JASP even can be better than SPSS, can gives you additional options than SPSS, although it can have some limitations for other types of logistic regression. And also, you can also check your influential outliers. If you tick case-wise diagnosis, Cook system, it also can check the influential outliers for you. So everything I think is okay now. We don't need anything else. That if we now have everything that we need to test our hypothesis. So we first start with the model table, model summary. So the omnibus test should be significant. That is like chi-square, this test, this value should be significant. We expect that to be significant for the model 1, not model 0, model 1, that is the model that you are, and you can see that is highlighted with another color. So this row is important. If the chi-square here is significant, that can show that your model is generally significant. It doesn't mean that all of your predictors are necessarily contribute to this model, but your model as a general model is fit and is significant. And the next variables that you, indexes that you can interpret is AIC and BIC. So these variables are, although they don't have any direct significance level, but generally, the lower they are, the better. And this especially can be helpful if you run multiple versions of your model. For example, if you run another model with removing some of your predictor, like keeping some of the strongest predictor and removing the weak one. And then if you want to compare the fitness of these two models, the ones with lower AIC or BIC in this row, those models are better fit because the lower they are, the better for a model. But in a single model, they may not be very informative because there's nothing that you compare with. And the next one also, the other variables that you want to uh, interpret here can be these ones, like the ones that you have 4 measures of R squared, that all of them actually can be beneficial, but there are just different measures of R squared that actually very similar to the interpretation of R squared that we have in multiple regression. That means it shows that all of your predictors together, how much of the variance of your DV they can predict. For example, they can show that, and usually I can also say that there are all are good to give you a range of R squared, but this one, this Nagel Kirke, if I pronounce correctly, it has very hard pronunciation. This one is usually considered by literature as the most robust one. So if you want to choose one to report, I would suggest to report this one. And for example, you can show that 49% of the variance of your DV, like depression level, clinical depression level, can be explained with all your IVs together. Very similar to the interpretation that you can see in textbook for R square for a multiple linear regression model. And the next thing that I wanted to explain, I'm just having a look on my notes to make sure that I haven't missed any points that I wanted to explain for interpreting the results. So soon after, yes, I think that's all. There's nothing else coming to my mind that you can report in your results section for this table. But soon after discussing the R square is the best, and also you should specify with this label. You shouldn't just refer to that as R square because it's very specific type of R square that you should always use this term, this complete term to refer to that. And so after that is the most relevant statistic is the coefficients, the individual. So now you know that generally your variables can predict your outcome variables. Your independent variables can predict your outcome variables. But coefficients can show the individual contribution of each of your independent variables. So in this table, we start with estimate. Estimate means unstandardized regression coefficient for each of your independent variables. And in addition, associated with estimate is very important that you report the Wald statistic. Wald statistic is to check the significance of each regression coefficient and also odd ratios as well. So the statistic of odd ratios and estimates is tested based on the p-value for Wald, for the relevant Wald statistics. For example, the significant values here are not directly for the B value. Like for example, this one is actually shows that the Wald statistic is significant. But when Wald statistic is significant, that means that you can consider your regression coefficient and odd ratio also significant. It's very similar to the function of T statistic in multiple linear regression that you usually report estimate T and significance together for like a multiple linear regression. And here you also report estimate, odd ratio, and Wald statistic, and then the significance of them, and also confidence interval to show the significance. So that is the function of Wald statistics. And the next and the most important value in this table is odd ratios. So they are the most essential values for your hypothesis testing. Odd ratios less than 1 or more than 1 is likely to show a significant prediction. However, the closer odd ratios are to 1, to value of 1, they are more likely to be non-significant. For example, you can see that for the ones that are not significant here, you can see that the odd ratio is 0.98 because it's very close to 1 is not significant because the closer to the 1, to the value of 1 they are, the effect size becomes smaller. So they should actually have a gap to 1. Either, for example, can be either 0.015, sorry, 0.15, for example, can be a very strong odd ratio because it has a good distance from 1. For example, odd ratio 1.95, for example, can be a very strong odd ratio because it has a very good distance from 1. For example, here also you can see that it's not very distant from 1, like just 0.4 percent, like it can be above 1, but it's still significant. It's a small effect, but it's still significant. So that is one point about odd ratio. Another point about odd ratio is that if odd ratio is less than 1 and is significant, for example, I can give you an example here, like that being significant, like for example, here is still less than 0.5. So like this odd ratio that is less than 1 and is significant, that means that there is this represent a reverse or negative prediction. That means that higher levels of this IV can predict a lower possibility of the DV, that is a clinical level of depression. But if odd ratio is higher than 1, like for example this one, and is significant, that can show that there is a direct or positive relationship. That means that higher levels of this IV can predict higher levels of higher possibility of having a clinical level of depression. And it's also very, very much the easier way to understand direction definitely is this, because it's always consistent with the direction of your regression coefficient. For example, here odd ratio is less than 1, and you see that the direction of estimate is negative, is higher than 1, and the direction of uh, estimate is, higher than 1 is here, like, and the direction of the estimate is positive. But for significant one, if it's not significant, you may see a contradiction, but so it's not significant anyway. So for example, in that case, it's not a problem. And and how to interpret now the results? So we can, for example, the simple interpretation is that you can say that, for example, you see IV1 is significant, the odd ratio. You can say that higher levels of IV1 is associated, because it's a negative prediction, higher levels of IV1 can significantly decrease the odds of clinical levels of depression, because here our possibility, our outcome that we want to detect is clinical levels of depression versus non-clinical levels. That means that our first variable, independent variable, is a protective factor. For example, it can be something like social problem solving skills, that higher levels of social problem solving skills can reduce the possibility, the likelihood of having a clinical levels of depression. However, this variable, for example, the IV4, has a positive and significant prediction. That means that it's a risk factor. That means that this is a pathological variable potentially. Like it can be, for example, like higher levels of early maladaptive schemas. That means that higher levels of early maladaptive schemas can significantly increase the odds of clinical levels of depression. So this is what is the simple interpretation for that, and that is good enough for your results section. However, if you want to be more precise in presenting your results or interpretation, you can also change the odd ratios to percentages of changes. For this, like for example, you can say that if 1 unit in your IV increase, how percentages in your, how percentages in the odds can be increased or decreased to predict your outcome variable. I can clarify that better with an example. For example, for this, firstly, to change the odd ratios to percentages and discuss your results based on the percentages, you need to subtract each odd ratios from 1 and multiply the results by 100. So subtracting each odd ratio from 1 and multiplying that by 100. For example, for IV4 that we have here, The odd ratio is 1.04. And if I do this calculation that I just mentioned, it can change this odd ratio to the percentages of 4.3%. So it can be the percentages of that calculation that I can get from that calculation is 4.3%. So how I can interpret that? I can say that for each unit of increase, for each unit increase or 1 unit of increase in IV4, this can significantly increase the odds of clinical levels of depression by 4.3%. That means that if I have 1 level of increase in IV4, the odds of clinical levels of depression can be increased by 4.3%. It's still a very limited percent, it's less than 5% increase in the odds of clinical depression, but it still is a significant level. So that means that although just for 5% it increased the possibility, the odds of clinical depression, but it still is a significant level. So in this way, it gives a more, I can say, a more practical measure of increasing the odds. For example, this can be still meaningful, like saying that this is the odd ratio, because you know that the odd ratio of 1 means that no significant possibility, definitely. That means that it's 50-50. It's just by chance that someone can be depressed or not depressed. But as long as it's higher than 1, that means that there is some possibility that can be actually a person having the uh, falling into the category of clinical depression. But when you change it to percentages, it can give a little bit more practical view that making that outside the context of like interpreting based on below 1 or higher than 1. But again, it's optional. It doesn't mean that you have to do that. And also, please note that in some textbook, uh, they also may suggest other ways to calculate and interpret the percentages of odd ratios. But these ways, the ways that you see in some statistical textbook will not provide such a clear interpretation that I provided now. Like you can say that 1 unit of increase in your IV can be associated with these percentages of odd ratio. However, they are also acceptable. If you follow other guidelines, you just make sure that your terminology, your sentences is completely consistent with those suggestions. And also, in general, it's not a big deal to change it to percentages. You can just interpret it as simple as what I explained earlier, like higher levels of IV4 can significantly increase the odds of clinical depression. So they can be as simple as that. And another table is this table is about just assumption check, like assumption of multicollinearity. And you should be familiar with that based on multiple linear regression. It's very much pretty much the same. That like as long as your VIF, for example, is less than 10, that means that there is no multicollinearity and your assumptions are met. And you can see that they are way below 10. So that means that there is no concern with the assumption of multicollinearity. And the next one is influential outliers. So this table would include only influential outliers based on the coexistence measure. If any participant have a coexistence value equal or bigger than 1, they will be shown in this table. However, as long as this table is empty, that means that there is no influential outlier for this specific model. And therefore, you don't need to remove any participant just for being an outlier. That means that even if your descriptive statistics show that there are some participants that might be outlier, these results show that they are not influencing these results. So you don't have to exclude them. So as long as they are not appear in this table, you don't have to exclude those participants from your table. And the final part that we can interpret for our result is confusion. table or confusion matrix that can be also have other names in other analysis output like SPSS. But in JASP, we call it confusion matrix. So it's also not a very essential statistic to report, like in many publications is not reported, but it's an optional step if you want to make your results section more comprehensive. So what is it about? This is pretty much based on the concept of like false positive or false negative tests that you are all familiar based on the medical test language or medical test kind. For example, if you do a blood test, and they say that is negative, that means that your hypothesis was that you may have like diabetes or you might have a certain disease, but this blood test is coming negative. That means that so this is no actually your prediction was wrong, and so there is no disease. You are not falling into that clinical level. And like if it's positive, that means that you have that condition. So it's pretty much the same in the context of our analysis. So positive actually here, that means that, for example, if you predict that a participant should be in falling into clinical level, and your model actually can categorize them correctly in the clinical level, we call them true positive rate, and which is appear here, and we call this sensitivity. So sensitivity, that you can see the value here, like 62, that is actually taken from here, means that the how strongly or how accurately your model can detect true positive cases. So it means that 62% of the participants were correctly detected to be in the clinical category, like we correctly detected them to be actually clinically having clinical depression. Actually, this model can do, because in our actual data set, we knew that which participant has a clinical depression, which participant doesn't have a clinical depression. But these variables, these independent variables, have the power to 62% correctly predict the status of clinical depression for a participant. The opposite of that is a specificity. Specificity is about true negative rate, that when the participants are not clinically depressed, this model with this pattern of variables can correctly predict, can correctly detect those participants that do not have clinical depression. We can correctly label them based on these predictors that don't have clinical levels of depression. And you can see that a specificity level here is 87. That means that 87% of, for 87%, this model could correctly detect participants with non-clinical depression and can allocate them correctly to the non-clinical category. And overall, we have also have an overall accuracy, that overall, like across sensitivity and specificity, our model, this model can be accurate for 78%, or for like more than 78%. This accuracy level can increase, could be increased if our predictors were a stronger predictor, or if even we remove some of the insignificant predictors from these models and have a better combination of predictors, better pattern of predictors, we may be able to increase like this sensitivity rate. We may be able to increase this overall accuracy rate. However, this is already acceptable. I can say that 78% accuracy is already a good percentage of accuracy for this model. So that's all you needed to report for binary logistic regression that can be comprehensively tested and reported in JASP. And also, and when you learn, if you are now familiar with all of this way of interpretation, you can easily now interpret other types of logistic regression as well, because they are very similar in interpreting this index with some slight differences. So now I'm going to explain the ordinal and multinomial logistic regression. However, again, I am suggesting you, if you are don't want to use binary logistic regression and you insist on using ordinal and multinomial logistic regression, I suggest using another software, like for example, SPSS or other softwares that can do that, because JASP is still the current versions of JASP cannot do the advanced analysis for ordinal and multinomial types of logistic regression. And you can see even they don't have the option. You should go to generalized linear model to be able to do that. And so you go here, you put, here you cannot put the binary version of your dependent variable. You should send the multinomial version of, or ordinal version of your dependent variable here, that for example, depression with 4 levels. Don't worry about this error. It will be fixed soon. Just, and also I need to send my uh, continuous independent variables to covariates. And to remove this, I need to specify my model. So in family test, go to other. And then you can see it's by default is multinomial logistic regression. But I want to test the ordinal logistic regression first. So change it to ordinal. And unfortunately, you don't have a lot of analytical options here. You just can, for example, tick deviance goodness of fit. That is very similar to what you checked already for binary logistic regression and confidence intervals. PS1 is not this similar. So I actually I had to cut a large portion of this video because I actually explained in this video like multinomial and ordinal logistic regression in JASP that I can show you. Where is the file? So explain still in details all the analysis that if you wanted for any reason, you had to use that for your results section and you wanted to report that. I explained that how to use it, but later I noticed there are some bugs actually in the results. When I compared that to SPSS, I noticed that there are apparently some bugs in current function of this analysis in JASP that maybe need to be fixed for the newer updates of JASP. And it was not the first time. JASP also had this history of bugs in some of the analyses in the previous version that they fixed it for the newer version. So that's why, for that reason, I would not recommend to use JASP for ordinal or multinomial logistic regression. JASP is the best, I can say even better than SPSS for running binary logistic regression, like using this function. So if you are happy to go ahead with the binary version of your dependent variable, JASP is the perfect option for that. However, JASP is not a good option, and not at least at the current versions are not a good option, does not give you the minimum statistics that you need for ordinal or multinomial logistic regression. Although the options are there, they don't give some essential statistics, and also they don't give you the uh, like, and also there are some bugs in the results that can be misleading for your hypothesis testing. So I just removed maybe 1 hour of explanation, but it's okay. I just don't want to mislead you or give you some type of analysis that are associated with bugs or may not be acceptable by the examiners of your report when you cannot report enough statistics. So, but I'm just going quickly to check you. If you want to like use binary logistic regression and want to run covariates, how to do that. So you know now how to run the typical analysis for binary logistic regression. For example, you have the binary dependent variable, and then these are also your IVs. And imagine that, and also like checking everything, I think they should be ticked already. No, they are not, but it's okay. We just tick them again, but we don't, maybe don't tick everything at the current moment, just some essential one. And then So how to, and now imagine that this time I want to control the effects of the confounding effects of gender and marital status as my covariate. So if I want to do that, the only thing I need to do, I just add them as additional predictors. So for that, if I consider, are they categorical or continuous? So gender and marital status are categorical, so I include them as categorical predictors. For example, if I wanted to include age as a covariate, I could include them here. So because it's a continuous variable. So, and after that, this is the key part, that everything that I want to be controlled as a covariate, that covariate is not moderation analysis. That means that even if they have a significant impact on my results, I'm going to exclude that impact. I'm going to adjust my result after accounting for that impact. So here I put my covariates or confounding variables, gender and marital status, to model zero. So not an interaction, just gender and marital status. So now in my analyses, I also don't care what is the results because they are not my main variables, they are just covariates. I just want to control their effects on my results. So now everything is the same. I just go to check like model one is my model that is based on adjusted. And also in model one, also I'm focused on independent variables. And now every odd ratio, every like estimate, everything that I have here is based on, oh, sorry, did I forget to add odd ratios? Yes, so now I had forgotten to add ratio. For example, now the odd ratios that I have here, hopefully, if it can show me the odd ratios. Uh, Yes, odd ratios. So odd ratios that I have here now for my independent variables, I can call them adjusted odd ratios because now they are adjusted after controlling the confounding effects of gender and marital status. Also, if I want to see that, I don't have to report this. Usually the publications don't report that. But if I want to also see if the gender and marital status had any confounding effects on my results, I can see that if they had a significant results here. For example, I can see that no, none of them had a significant except this last one, that is marital status, other variable. So also you can see that not all levels of gender and marital status are included here. For example, I have male, non-binary, not female here. That means that female is considered as a reference variable. So if I want to interpret that, but I don't have to in publications, they usually don't do that. But if I want for any reason interpret that, I can say that, for example, non-binary gender compared to female gender, for example, can have a significant result. Like when I compare non-binary gender to female gender, if it is significant, that means that it is a significant confounding variable, a significant individual differences between those who have non-binary gender and those who have female gender identity in like these levels of depression. So, and also based on this model, in this regression model. So, in that case, I would consider that gender might have a significant confounding variables, specifically when comparing like a non-binary with female gender. It could be for male one. So, but none of them are significant. But here for marital status, other is significant. That means that those who, because you see that here the odd ratio, oh no, for others also is not significant. So I thought that for a moment it was significant. But in the second model, potentially, yes, the second model actually you can see that the others might have shown. No, here also, not I was just sorry, I was looking for the wrong column. So none of them actually are significant. But if any of them were significant, I would interpret in that way. But usually in publications, even if they are significant, they don't report that. They just say that after controlling or accounting for the effects of gender and marital status, the adjusted odd ratios was like this. So that's as easy as that you can control covariates if you want to include that. Again, it doesn't show anything about the moderating effects. It just can suggest future research to investigate individual differences or moderating effects of these variables, because your research can show that they potentially can have confounding effects on data, but no concern for your results because you have already controlled the potential effects of that. And we can call our model as an adjusted model, and we can call our odd ratios as an adjusted odd ratio. So if you've seen some publication, they use these terms. This is because they have controlled some covariates in their model. So that was all for logistic regression. And so I think you have now everything that you need to write a strong uh, results section based on logistic regression.